Hello, welcome to Daoud Academy, where you'll find quality educational resources to enhance your performance in school that will aid you for your performance in university and college. In this video today, I will be going over how to calculate the estimate of the instantaneous rate of change and how to calculate that. Just before I start, I'd like to ask you if you have not visited this channel before and haven't subscribed, please do subscribe below. Click on the subscribe button and click on the bell notification icon so that you may receive any videos that I post. I will do many more videos in the future pertaining to math, sciences, and other courses as well, but more as a educational resource and library for yourself, so you can refer back to these concepts when need and on demand. It's very useful to be refreshed constantly with new concepts. When you're uptaking new concepts, to refresh with older concepts that may be the building blocks for the more advanced math or science that you're taking now. So please subscribe, and that'd be great. And if you have any comments below, please comment at the end of the video. And let's get right to it. So today we're going over how to calculate an estimate of the instantaneous rate of change. Now, the previous videos, if you've been following, we've been calculating the average rate of change, and prior to that, I went over somewhat a detailed explanation of what are the rates of change and how do we calculate them, what are their meaning, where do we see them. So if you want to refer back to those previous videos, I'll be including them at the end of the video, and you can check now as well. I'll include a link to the videos pertaining to the rates of change. So today, what I'm going to start off with is a basic function. And from that function, we're going to calculate an estimate of instantaneous rate of change. So if we remember, the instantaneous rate of change is basically the slope of the tangent line crossing through one point on a curve. This will help us to understand when one parameter, y, is changing with respect to x. So as you all remember, x is the independent variable and y is the dependent variable. So x really changes. As x changes, y will change according to how x is changing. So y is dependent on x. Let's start off with a basic function. I will start off with, let's say, an exponential function f of x equals 2 to the power of x. So starting from this function, we can create a table of values, and we just need some key points. We know it's an exponential function, and exponential function has a horizontal asymptote. Horizontal asymptote is at y equals 0, so you can state that first. That's the equation of the horizontal asymptote, y equals 0. We can draw that, just change this color to red, and draw a dotted line. This is our horizontal asymptote, dotted dash line, representing the horizontal asymptote. Now, y equals 0, and then we have the x-intercept. Sorry, there is no x-intercept, there is a y-intercept. So y-intercept is when x is 0. And that happens at 2 to the power of 0. We know that would give us 1. 2 to the power of 0 is 1. So the y-intercept is at 0, 1, typical of exponential functions with no leading coefficient. So we'll just state that here. This is our y-intercept. I'll just change this to yellow. Okay, so we have the y-intercept, and we can create a table of values. So from this table of values, we can determine some points. So let's choose some points in the negative. We know y cannot be 0. 2 to the power of any number can never give you 0. So let's choose some points here for x and y. So let's choose negative negative half. And we'll choose, 0, and then we'll choose 1, and we'll choose 2. Those 4 points. So let's start with x equals negative half. So you end up with 2 to the power of negative 1 over 2. Now you have a fraction in the exponent, and it has a negative symbol, so we can represent this in terms of a positive exponent by flipping the value or finding its reciprocal. So remember this would give you in order for you to change this negative exponent to a positive, you just need to bring that whole term down to the denominator, make it into a fraction. So we have now 2 to the power of 1 over 2, and whenever you have a rational or fraction in the exponent, this represents a radical expression. So radical expression being the denominator of the radical expression here is the root value, and the numerator is the power. So if you remember this would become 1 over the square root of 2. Okay, so 1 over root 2. And we can get somewhat a decimal value for the square root of 1 over root 2. So 1, excuse me, 1 divided by root 2. This gives us 0.707. So 0.707. We can represent this here as an approximation because this is somewhat a sketch that we're trying to draw. X equals negative 1 over 2, so this is negative 1, that's negative 1, 2. Negative 1 over 2 would be in between here, and 0.77 somewhere on here. Again, this is just for a sketch. You can be more approximate if you have grid paper or if you're using like decimals. And then we can continue with the table of values when x is 0, y is 1. So we have that point there, and x is 1, 2 to the power of 1 is 2. So when x is 1, y is 2. And then draw that. And when x is 2, y is 4. That would be 4, somewhere around here. Great. So what we end up getting, I'm just going to sketch this maybe with a green color. We end up getting a graph something that looks like this. So we know it's an exponential function, and the base is 2 to the power of x. So now we want to find instantaneous rate of change. Let's say we wanted to find instantaneous rate of change at x equals 1. So x equals 1, that represents this point right here. So that point, if we drew a line crossing that point, choose a liquid color. Oh, sorry. Let's just go down here. So this is a line that passes through only that point on the curve. And from here, I want to determine the slope of that line, or not the exact value, because doing that we need to go through another process called the difference quotient. But today in this video, we want to go over how to calculate the instantaneous rate of change or the slope of the tangent across that one point using some other methods. So we already know the function. We also talked about calculating this graphically in the previous videos. So graphically, if this was on a grid paper per se, once you draw the line of the tangent, or that tangent line crossing that point, on a grid paper, you just have to choose 2 points on that line, any 2 points. You try to find ones that are passing through the exact intersections of the grid line on the grid paper, and then that would give you somewhat a good approximation. Again, it's not accurate because my perception of a line is different than your perception of it. If I slightly have, let's say, 0.5 degrees slanted down on a decline, and you may have your line may look at 0.5 degrees on on an incline. So the calculating instantaneous rate of change using a graphing method has definitely its limitations, but if the graph has been done properly on a very precise grid paper, you get a very good approximation. So again, you just need to draw the slope of the tangent as accurate as possible to your perception. Again, there's human error involved there. And you just choose 2 points on that line, and you get the slope of those 2 points. That would give you the slope of the tangent graphically. But today we wanted to go over methods that we can get an approximation mathematically, or using the calculation or the function. So what I'm going to do now is going to erase this portion, and we're going to calculate how to get the instantaneous rate of change using the first method, the preceding following method. So the preceding following method, what we're going to do, I'm just going to use my spotlight here, is this is the point of interest, right? This is the slope. We want to find the slope of the line crossing across that one point. But if we can use a method where we find the slope of the average rate of change, or the slope of the secant across 2 very closely associated points, one to the left of x equals 1 and one to the right of x equals 1, and we get that value, okay, get the value of the slope before the preceding average rate of change from the point of interest, and then the slope of the secant after, or the following of x equals 1, then we can get 2 average rate of change that are very closely close in proximity to the point of interest. We get those 2 values, we add them together, and we divide it by 2. So that would give us a good way of getting an approximation of the average rate, instantaneous rate of change at x equals 1. So let me just, to be more specific, let's change our, so let's say we know that this is x equals 1. I'm going to choose my first 2 points. One is going to be 0.9 and one is going to be at 1. So we're going to start first by finding the slope of the average rate of change between x is 0.9 and x is 1. So how do we do that? If you remember, the average rate of change is y2 minus y1 over x2 minus x1. So we already have the point for at 1 comma 2. Sorry, x equals 1, yeah, so 1 comma 2. So we have that first point. That's 1 comma 2. That's our first, or that'll be like our second point. Let's call this point B. And point A is at x equals 0.99, or 0.9, sorry. So x is 0.9. We just chose that arbitrarily. You could choose 0.85, you can choose 0.95, 0.99. The closer, the better. But this is just to give a visualization of what we're doing here to get the average rate of change, sorry, the instantaneous rate of change, by using average rate of changes for the preceding and following intervals. So 0.9, x is 0.9, we need to calculate manually using the calculator f of 0.9. So in your calculator, you just have to sub in 2 to the power of 0.9. So A is going to be 0.9. And then we just have to calculate this in our calculator. So 2 to the power of 0.9 is 1.866. 1.866. So then we have 2 points now. The first one is A, 0.9, comma 1.866. The second is our point of interest where we were trying to find the slope of the tangent, is B, 1 comma 2. And then we just go forward to the calculation of the slope of the first average rate of change. We call this IRC1 for the preceding. Y2, so in this case Y2 is 2, minus Y1 is 1.866. over 0.9, 1 minus 0.9. So x2 minus x1. And we just punch this into our calculator. And 2 minus 1.866 divided by 1 minus 0.9. So you get 1.34. You just need to calculate that, 1.34. Okay, so now we've calculated the average rate of change for the preceding interval. Now I want to find the average rate of change for the following interval. So the same way that I chose x equals 0.9, so I decreased from x equals 1 to 0.9 is a decrease of 0.1. On the following interval, I'm going to increase from x equals 1 to x equals 1.1. So let me just erase some portions just to free up the whiteboard. So you can just go back to the video, I guess. I'll just erase this portion just to free up more space. So now my A point becomes 1, comma 2. And my B point excuse me, my B point becomes 1.1, comma f of 1.1. So we need to calculate what f of 1.1 is. So f of 1.1, we have to put that in the calculator, is 2 to the power of 1.1. We need to do a calculation. So 2 to the power of 1.1. is 2.143. And then now we're going to find the average rate of change on the second interval, on the following interval, MARC2. Again, y2 minus y1 over x2 minus x1. In this case, y2 is from point B, so it's 2.143. And minus 2, so y1 over x2 minus x1. So x2 in this case now is 1.1 minus 1. So this would give us 0.143 over 0.1. So 0.143 over 0.1 basically is 1.43. So now we have the average rate of change on the preceding interval and the average rate of change on the following interval. To find the estimate of the instantaneous rate of change when x equals 1, we just have to take those two intervals, we're going to add them up, and we're going to divide it by 2. We're going to get those two values, add them and divide it by 2. Technically, this represents that the instantaneous rate of change, that slope of the tangent, is the midpoint, or is the middle component found between those two intervals. So you found this interval between the preceding value to the point of interest, then you found the slope of the tangent. So sorry, the average rate of change from the point of interest to the following interval. Take those two numbers, which is a slope, add them together and divide it by 2. This gives us a midpoint calculation for the instantaneous rate of change. So we can find the instantaneous rate of change estimate, so I'll put EST, is 1.34 plus 1.43 divided by 2. Just add that up. 1.34 plus 1.43 divided by 2. This gives us 1.325. And this is basically the method to calculate an estimate of instantaneous rate of change using the preceding following method. It is time consuming. There is definitely faster ways. When you get to actual calculus, you'll know how fast it is to calculate the instantaneous rate of change accurately, an exact value. But in this case, we're trying to find a method using an estimation process using, as we mentioned, the preceding following method. So in my next video, I'll be going over calculating an estimate of the instantaneous rate of change using something called the centered interval method. And then following that video, I'll be going over how to calculate, again, an estimate of the instantaneous rate of change using the decreasing interval method. So it's a right-handed method, right-handed decreasing interval concept of calculating the instantaneous rate of change or estimate of it. And then finally, after those, I'll be going over the how to calculate the actual value for the instantaneous rate of change at any particular point along any curve using the difference quotient. And we'll go over some concepts there where the point is given, where point is not given. We have the function only, and we want to find the actual function that will determine the instantaneous rate of change along any point on that curve. So if you like this video, please give it a thumbs up and subscribe to my channel if you like the content. If you have any comments, please leave them below. I love to read comments and reply as well. And furthermore, I just hope that this channel becomes a great resource for you and inspiring you to love going to school, solving problems. And remember, these are the building blocks for more complicated problems down the road. And it's always a good reference to look back and see how to calculate these smaller concept problems or smaller building block problems and build your knowledge, keep it solidified, as even when you're in upper year mathematics courses or higher education. So thanks a lot, guys, and I'll see you again in the next video. Bye. Take care.